Okay, this is part two of a two-part lesson on circuits and Kirchhoff's laws. In the last lesson, we looked at rules for combining resistors and figuring out equivalent circuits with equivalent resistance. In this mini lesson, in this part of the lesson, we're going to be taking a closer look at Kirchhoff's laws themselves to see how we can use Kirchhoff's laws to study networks of resistors and batteries in more complicated circuits. So all the images you see are attributed to OpenStax College of Physics, published by openstax.org, distributed under the Creative Commons Attribution License version 4.0. Okay, so let's take a look at this circuit. This circuit has two batteries, E1 and E2, and 5 resistors. Little r1, little r2, r1, r2, and r3. So we're going to interpret little r1 and little r2 as the internal resistance of the batteries, and E1 and E2 as the electromotive force supplied by those batteries in units of voltage. So we could do some work on this circuit to combine resistors that are in series to simplify it. For example, we could combine these two resistors and these two resistors and simplify this to a circuit that's simpler. But we could also study what's going on in the circuit using Kirchhoff's laws, which, as we'll see in the next few slides, Kirchhoff's laws are laws which are basically statements of charge being conserved and energy being conserved as electrons or current move around the circuit. All right. So first, let's look at Kirchhoff's junction law, or Kirchhoff's current law, which I abbreviate KCL for short. This law is essentially a statement that charge is conserved, and current is moving charge. And what this law says is that if you have a junction in your circuit, that's a place where wires come together or go apart, the total amount of current, let's write as sigma I, coming into that junction has to equal the total amount of current that's flowing out of that junction. So for this particular example right here, we see I1 is flowing into this junction. So that must be equal to the sum of I2 and I3, which flow out of that junction. So Kirchhoff's current law, or Kirchhoff's junction law, KCL, allows us to write down algebraic expressions for the currents flowing into and out of junctions in circuits. And this is the general statement of what the law is all about, and this is what the application of this law looks like for this particular circuit right here. Okay, next up is Kirchhoff's loop law, or Kirchhoff's voltage law, which I abbreviate KVL for short. Now this law is a statement that energy is conserved. And if you recall, voltage is electric potential energy per unit charge. So Kirchhoff's loop and voltage law is a statement that voltage is conserved in electric circuits. Now in practice, what this means is, in words, that if you have a circuit like the circuit shown here, and you go around that circuit and complete one loop ending up back where you are, you encounter a bunch of different components. So here you encounter a battery, then a resistor, then another resistor, and finally a third resistor, and then you end up back where you belong. So Kirchhoff's loop law, or voltage law, says that as you go around the loop, the voltage changes that you encounter when you cross over various components, whether they be batteries or resistors, have to all add up to 0. This is sort of like saying that if you go on a hike and you start at the bottom of the hill and you hike up to the top of the hill, and then you come back down, you do go around the forest and come back, and you end up where you started, your gravitational potential energy where you started is the same as where you ended because it's the same place. If you add up all the changes in your gravitational potential energy on that hike, you end up with 0 because you end up where you start. So in circuits, if you add up all the voltage changes as you go around the circuit, they have to add 0. They have to add up to 0. That's what Kirchhoff's voltage law is all about. So we can say this compactly using mathematical notation as the sum of the changes in voltage as you go around a loop is equal to 0. Now this figure down here shows another way to visualize what's going on here. Here, the voltage at different parts of the circuit is visualized by the height of this yellow bar. So if you start at the negative terminal of the battery and cross the battery, the voltage increases, and then when you cross this resistor, the voltage goes down, and then it stays the same until you get to the next resistor where the voltage drops again, and the voltage drops again at the final resistor, and you're back at 0. So the height of this yellow bar represents a change in energy or a change in voltage, and the changes cumulative around the entire loop add up to 0. You're back where you started. Okay, so how do you actually calculate the voltage changes when you encounter a resistor or a battery in the circuit? Well, batteries are easy. Batteries are voltage sources. So if you're traveling around the circuit and, let's try that again. If you're traveling around the circuit and you cross a battery and you cross it from the negative side to the positive side, like here, then the voltage is going to increase and be equal to the voltage of the battery. But if you're traveling around the circuit and cross a battery from the positive terminal to the negative terminal, then the voltage decreases and is equal to the voltage of the battery. Okay, now what about resistors? Well, we can calculate the amount of voltage that a resistor uses by using Ohm's law, V equals I times R. So the voltage used up by a resistor is equal to the current that flows through it and the resistance, electric resistance that the resistor supplies. Okay, now what about the direction that you cross the resistor? Well, in this case, you need to pay attention to the direction that current is flowing through the resistor. So if you cross a resistor, if you're going around a circuit, applying Kirchhoff's loop law, and you cross a resistor traveling with the current, then that's like water rolling downhill. You're losing voltage. You're going to lose voltage. On the other hand, if you cross a resistor going against the direction of current, that's like going uphill. It would be like you going up a waterfall and encountering water that has more gravitational potential energy at the top than at the bottom. You're going uphill in terms of voltage, and when you're crossing a resistor going against the flow of current. Okay, so just to summarize here, if you're traveling around a circuit and you cross a resistor in the same direction the current flows through that resistor, that's going to result in a voltage drop, a negative IR of voltage change. If you cross the resistor in the opposite direction the current flows through that resistor, that's going to increase. That's going to result in an increase in voltage, a positive IR change in voltage. Okay, so let's put these rules into practice with this example circuit right here. Okay, so this circuit has 4 resistors, and it has 1 battery or power supply, 1 voltage source equal to 90 volts. All right, so the first thing I'm going to do is I'm going to look at the circuit. I'm going to guess at the direction the current flows in the various branches of the circuit. So it makes sense that current's going to flow out of the positive terminal in the battery. So I'll call that I1. And then when I get to this junction right here, the current splits. Some of the current flows down through R1, and some of it's going to flow to the right through R2 and R3. So I'll call that I2 and I3. Okay. So I might be wrong. I've assumed that the directions of the currents are as indicated here, but I might be wrong. And if I am wrong, the mathematics will tell me that I'm wrong in the end, because I'll end up with a negative value for a current if it actually flows the opposite direction of what I've assumed right here. Okay, so we don't have to worry about that right now. All right, so I3 flows around this circuit. It's going to flow through R2 and R3, and it's going to come down here, and then when it gets to this junction, it recombines, I3 recombines with I2 to give us I1 again. All right, so let's focus on junction B here and apply Kirchhoff's current law. Junction B has I1 flowing into it and I2 and I3 flowing out of it. So Kirchhoff's current law, or junction law, says that I1, the total current flowing into that junction, has to equal I2 plus I3. Okay, now what about the loop law? Well, this circuit actually has 3 different loops. There's an outer loop, then there's 2 inner loops. And I can choose to go around each of those loops counterclockwise or clockwise. So I've just drawn everything clockwise. So what I'm going to do here is it turns out that only 2 of these loops are unique, because I can get the third loop by combining the other 2. For example, I can get the outer loop by adding together the left loop and the right loop in the inner part of this circuit. Okay, so I'm going to stick with the 2 inner loops, call them loop 1 and loop 2. All right, so I'm going to start with loop 1, and I'm going to start right here, right before the battery, and then I'm going to go around this loop clockwise. So as I go around this loop clockwise, the first thing I cross is the battery, and I cross it from negative to positive, so the voltage is going to increase. So the voltage change crossing the 90-volt battery going from negative to positive is plus 90 volts. Okay, so I've crossed the battery. Now I'm going around, I'm going around, I'm going around, and then the next thing I encounter is resistor 1. And when I cross resistor 1, I'm going with the current that's flowing through resistor 1, I2, so that's going to result in a voltage drop. I'm going downhill in terms of energy and voltage. And the voltage drop, according to Ohm's law, is the current flowing through that resistor, I2, multiplied by the resistance of that resistor, which is R1. Okay, I keep going, keep going, keep going, keep going, and then I encounter another resistor, R, and again, I'm going to cross that resistor in the sense of the current, in the same direction as the current that flows through that resistor, which in this case is I1, so there'll be a voltage drop equal to the current that flows through that resistor, I1, multiplied by the resistance of that resistor, which is little r. And that equals 0. The loop law says that the sum of those changes, some positive and some negative, equals 0. All right, so now let's take a look at loop 2. I will start loop 2 right here at the point labeled C, and I'm going to go around this loop clockwise. So the first thing I cross is R2, resistor 2, and I cross that resistor going in the same direction as the current that flows through that resistor, which in this case is I3. So that means there's a voltage drop equal to, as Ohm's law guides us, the current flowing through that resistor, I3, multiplied by the resistance of that resistor. Then I'm going to cross R3, and again there's a voltage drop, but this time equal to I3, R3. Okay, and I keep going and I keep going. I go up this branch, and the next thing I encounter, here's where it gets a little tricky, is R1. But as I cross R1 on my way back to where I started, this time I'm actually going against the current that flows through R1. So that means I'm going uphill in terms of voltage. So as the voltage change crossing R1 going against the current is going to be positive. and it's equal to, according to Ohm's law, the current flowing through that resistor and its resistance. And I keep going, keep going, keep going, keep going, keep going, and then I'm back to where I started at point C. The loop law says the sum of those voltage changes equals 0. Okay, so what's the use of all these equations? Well, if I look at the information that's given to me here, the things I know are the voltage of the battery and the resistances of the resistors. So in these equations, there's 3 unknowns, namely I1, I2, and I3. But now I have 3 equations, so I can solve for those 3 unknowns. General rule of algebra is that you need at least as many equations as you have unknowns if you're going to solve for the unknowns. So now it's a lot of algebra. We'll practice it in class, and you'll get practice in homework. But we could solve for I1, I2, and I3 by doing substitutions to eliminate the 2 of the unknowns in one of these equations, so we can solve for the third. All right, so that concludes this lesson. Again, in class, we'll do some more practice actually solving these equations that you get by applying Kirchhoff's current law and Kirchhoff's voltage law.